A very good evening, everyone. I'm Sandhya Shekhar. I'm the teaching assistant for this BT39 bioreactors course of this NPTEL series. We will be seeing we will be seeing the tutorial 2 of this week. We'll just have a quick overview of what we have seen in tutorial 1. If some of you guys have missed it in tutorial 1. Tutorial 2 that we are going to solve now will be helpful for you guys to solve the assignments that are being posted for this course. So just try to understand what I'm saying in tutorial 2 so that if there is any question you guys can post to me so that I can just solve and then get back to you guys. If these are being properly understood along with the lecture that you have seen in the NPTEL course, both will be more than sufficient for you guys to solve the assignments. Okay, so first we will get into the tutorial 1, what we have seen at first, and then we will move on to tutorial 2. Okay, yes. So what we'll just have a quick overview of what we have seen in tutorial 1. So that's it. That was the main motto of doing this. Okay. We were seeing which option best describes hybridomas. So we just understood that hybridomas are nothing but these are a fusion of plasma cells as well as myeloma cells. So the right option that corresponds to this is a fusion of antibody producing cells and cancerous cells. If you guys want to have a like a very explained topic about all these things, I have already uploaded tutorial 1 extended version. You guys can see that, so you guys will have a deep understanding of what each and every question corresponds to. But the sole purpose of explaining it here is just to have a quick overview of what we have seen in the last tutorial. Okay. Which of the following products that are commercially produced using bioreactors? And option B, insulin, monoclonal antibodies, antibiotics, biomass. Option 3, the media used for bioprocess is contaminated with single cells with thermal response characteristics. It has been observed that by maintaining the media at 60 degrees Celsius for 25 minutes, 85% of the cells become non-viable. Determine the decimal reduction point. So the decimal reduction point is nothing but time taken for a 10-fold reduction in the viable cell concentration at a given temperature, and this is the formula. So as we have to find out Kd, we have taken this formula T is equal to 2.303 divided by Kd log of xp naught divided by xv, and we have found out Kd, and when we substituted Kd further in the decimal reduction time equation, we just got the answer 30.35. Okay, moving on to question 4. Write the mass balance equation for microbial cells in a bioreactor under batch operation. So under batch operation, we know that there is no inlet as well as outlet of the cells. So the overall mass balance equation will be deduced to Rg minus Rd is equal to dA divided by dt. That is rate of generation minus rate of consumption is equal to rate of accumulation of the cells. So option C is the right answer. Match the following important components of bioprocessing. Recombinant E. coli corresponds to the inoculum, glucose corresponds to the substrate, and amylase corresponds to the product. Okay. The main factors to be optimized while designing a thermal sterilization processes are based on the data that is being given here, it is very much understood that it is a function of temperature as well as time. That means like n by n naught. N is nothing but the viable cell concentration at time t, and n naught is the viable cell concentration at time 0. So this is dependent on temperature as well as time. So those two answers has to be picked for this one. And identify the type of bioreactor where aeration and agitation is brought about by pumped air alone. So when we were seeing stir tank bioreactor where aeration is brought by sparger and agitation is brought up by the impeller. Okay, whereas in airlift bioreactor, both mixing, that is the agitation as well as aeration is brought completely solely by pumped air alone. Whereas in packed bed bioreactor, the purpose of using aeration is only to provide oxygen and there is no mixing in this. And similarly in the solid state bioreactor, the solid state feedstocks are being kept, and the purpose of using aeration is only to give aeration to the inoculum as well as all the cells, but not for mixing. So the right answer was airlift bioreactor. Dr. A is going to do a microbial experiment in the laminar hood. Which of the following she can use to sterilize the hood? So we have seen that the answer is UV lamp as well as 70% ethanol, as UV lamp can damage the DNA of the cells, as well as 70% ethanol can kill the cells by dehydration, protein denaturation. These two are being used as a combination. Match the following parts of bioreactors with their purpose. Sparger, that is used for aeration. Sparger can be used for agitation also in case of pumped air, like in case of airlift bioreactors. But in this case, in this match the followings, the sole purpose of using sparger is for aeration, and impeller is for agitation, devo sensor is for oxygen level. The last question of tutorial 1 was Dr. NX runs a bioreactor experiment and found that his process produces toxic byproducts, which are affecting cells viability when accumulated. Which of the following mode of bioprocess is suitable to solve this problem? Batch mode alone, continuous mode alone, fed batch mode alone, both fed batch and continuous modes. So we were saying that continuous mode is a preferred process for this, because your byproducts will be continuously removed from the media, okay, and the cells will be recycled back. So you will not have cell loss, not to certain level, whereas you will be continuously like moving your removing your toxic byproducts. But fed batch is also one of the right answers, because in case of batch process with a very high initial substrate concentration, what happens is that the glucose, for example, glucose being used at like 240 gram per liter or something, this will be going for what to say, all the other uh, like byproduct formation also, because already the acetyl CoA and other precursors are available in a very high concentration, so it has to be used by the cells at the appropriate time, and due to the feedback inhibition and all, it will not be going for your product of interest, and it will be evenly distributed for all other byproducts also. So that's where your fed batch comes into play, that we have to use an optimal concentration of substrate concentration during the batch process, and once the fed batch starts, we will be feeding the substrate in such a concentration that it will be just utilized for the cells for the targeted product formation, but not like diverting it for others. So with this we just finished our like tutorial 1. Now we will be seeing our tutorial 2. So now we are going to see BT39 bioreactors in PTL course tutorial 2 session. Okay. So the very first question is, which among the following is the cheapest carbon source for microbial culture? Option A, glucose. Option B, starch. Option C, glycine. Option D, ammonia. So we'll just get into the root of it. Let me take my pointer. Yes, glucose. So glucose is being used as one of the commonly used carbon source. Yes, it's a carbon source. So there are two things in the question itself. So one is cheapest. It should be cheapest as well as it should be a carbon source. So we'll just categorize it. Is glucose a carbon source? So whether it's a carbon source or not, and whether it's cheapest or not, we will see. Okay. Yes. So is glucose a carbon source? Yes. Okay. If you come to starch, is starch a carbon source? Yes. So we will compare at the end what are all the carbon sources that are being given and what is the cheapest among those. In that way we can categorize. Okay. Coming to option 3, glycine. Is glycine a carbon source? No. Glycine is an amino acid. This cannot be used as a carbon source. Okay. Glycine has other purpose, like if any oxotrophic mutants that cannot produce glycine on its own, that where we will be adding glycine as amino acid in the medium, so that the organism can utilize the glycine and then it can grow. In that way glycine can be given as a external supplement in the media, but usually all these are being present in yeast extract, tryptone, and all these things are like undefined media, right? Like we don't know what are the components in the tryptone as well as other media, but all these yeast extract, so all these has a certain amount of amino acids in that, and glycine is also present in all those. Okay. Ammonia. Is ammonia a carbon source? No. Ammonia is being used as a nitrogen source, like ammonium sulfate, ammonium chloride, all these are being used as a nitrogen source. So out of 4 options, first of all, glucose and starch are only the carbon source, the other two are not even being considered as a carbon source, right? So we'll see like which is the cheapest one. So whether it's starch or glucose. So we know that glucose is being used as a very commonly used carbon source for most of the microbial culture, whereas starch is not the commonly used one. But our question here is whether it is cheapest or not. So starch is nothing but it is abundantly available over in like for example many feedstocks, okay, many feedstocks like contain starch as the major in the major content, okay. So starch can be utilized as a used for waste valorization. So what researchers do is that they use many feedstocks, or else the waste that was generated from the feedstock, and that will be used for waste valorization, okay. So waste valorization is nothing but from the waste we will be producing some value added products from that, okay. So if starch is being present in any cornstarch and all these things we are saying, right? If starch is being present, that can be used as a microbial carbon source, and we can just do some enzymatic treatment, or else like even we can do amylase we can use for breaking down the glucose particle so otherwise we can do any thermal sterilization, or else like many heat treatment, or else any chemical treatment can be done so that the glucose are being broken down, like the higher component whatever the polymer is there, that will be broken down into glucose, and that can be directly used for the microbial culture, okay. So comparatively starch is the cheapest one compared to glucose, so the answer is starch, okay. Moving on to question 2. When the substrate happens to limit growth, which among the following is best for modeling the growth profile? So option A, Andrews and Knock model. Option B, Luedeking-Perrott model. Option C, Monod model. Option C, Jerusalimsky-Neronova model. Okay. So first we will just see whatever we know very well. So Luedeking-Perrott model we know very well. What does Luedeking-Perrott model denote? Rp is equal to alpha Rx plus beta X. Okay. So here we know that Rp is nothing but rate of product formation, right? So the Luedeking-Perrott model comes under the product formation kinetics. So this is not going to be related anyway to the question that is being asked here. So here what they have asked, when the substrate happens to limit growth, okay. For example, if glucose is being present at a very high concentration, what happens is that the substrate itself, due to the higher concentration, that will stop the growth of the organism. So glucose is one such example. If it is glucose, even sucrose also, if it crosses a certain concentration, that will be toxic for the cells only. Either the cells will become hypertonic or hypotonic, so that the cells will not be able to do the cell maintenance or whatever the normal activities that it has to do, that cannot be done, okay. And one of the main examples that I can quote is that methanol. In case of Pitchia fermentation, sorbitol, methanol, and all these things are all these are being used as a substrate. Sorbitol is an alcohol, and methanol is also alcohol only. When methanol is being present at a very higher concentration, that will become toxic for the cells to grow only. So it has to be always maintained at a certain concentration so that the organism will be able to use that as a substrate to feed and then grow. It will not be toxic for the cells if we maintain the saturation properly, okay. So as we were discussing here, Luedeking-Perrott model RP, this comes under product formation kinetics, and hence it is not our answer. So moving on to Monod model. Monod model says that mu is equal to mu m s divided by ks plus s, where we know mu m is the maximum specific growth rate and ks is the saturation constant. Here what they are saying, like in your question, in your equation only you can see Just a minute, I'll take the pointer. So in the question only, we are understanding that here they are just giving the relation between your substrate concentration to the specific growth rate. Okay, so this is not going to tell you in any way that how your substrate is going to limit the growth of the cells. So that is also not being given here. Whereas Jerusalemsky Neronova model, here if you see the equation, mu is equal to mu m s divided by ks plus s, kp divided by kp plus s. So kp is nothing but here your product saturation constant. Okay, so here they are denoting that your product inhibits the growth. For example, in case of lactic acid, as I already mentioned in the last tutorial, your lactic acid can inhibit, if it is present at a very high concentration, that itself will inhibit the growth of the cells. For example, I'll explain it one more time. Your fermentation is running, and the lactic acid starts forming in the media, and obviously when the lactic acid or acetic acid, formic acid, whatever forms in the media, the pH will drop down very slowly. Say for example, your optimum pH will be 7, and your as the lactic acid, formic acid and all these acids are being produced, that will drop down to almost 4 or 3.5. But as we are doing it in the bioreactor scale, by adding the base and all, we will be trying to maintain the optimal pH. But what happens is that the organism cannot take up lactic acid after a certain concentration. That itself will become toxic for the cells to grow. Okay, so that is called product inhibiting the growth itself. Okay, lactic acid is one such very good example. Even acetic acid also, formic acid also, all these can inhibit the cell growth itself. So moving on to option A, Andrews and York model, where mu is equal to mu m s divided by ks plus s, ki divided by ki plus s. So ki is the inhibition constant. So this inhibition constant denotes that substrate is inhibiting your like growth, cell growth. Okay, so the right answer is Andrews and York model. So whenever such questions are being posted to you guys, rather than like selecting something randomly, write down those equations, because these are being taught already in the classes, right? So write down the equation. If you just see, you might think like Monod model is the right answer also, but here in Monod model, nothing related to inhibition has been, no inhibition constant has been given in the equation itself. So in that way you can rule out this. Whereas in Dedekind Pirate model, you know this is going to come under product formation kinetics. Whereas you don't know what is Andrews-York model and the Jerusalemsky model. So you can categorize while studying what are the product inhibition kinetics, what are the substrate inhibition kinetics, and all these things while studying. If you can what to say, figure out, it will be very easy for you guys while solving the problems. Okay, just a minute. So moving on to question 3. Which of the following is true according to Michaelis-Menten kinetics? Option A, Km is dependent on enzyme concentration. Option B, Km is independent of enzyme concentration. Option C, Vm does not vary with enzyme concentration. Option D, Vm varies with enzyme concentration. So it's a very tricky question, right? Like it's very confusing, like while reading the options only, like which can be right, which can be wrong. We will not have any idea until and unless we write down the equations. Okay. So if you are not very comfortable with what they have asked, if you are not understanding the options properly, try to write down the equation. It will be very easy for you guys to understand like what can be the right options as well. Okay. So what is Michaelis-Menten kinetics? Mu is equal to mu max s divided by ks plus s. But with that, we will not understand like what is related to what. Sorry, V is equal to, that's Monod model, right? Sorry for my confusion. V is equal to V max s divided by km plus s. Okay, so here what is km? I will solve these equations. So here I have directly written what is Vm. Vm is equal to K3 Et, whereas Km is equal to K2 plus K3 divided by K1. So based on this, can you understand Vm is dependent on the enzyme concentration, whereas Km is not dependent on the enzyme concentration. So where is it? Yeah, Km, that is right. Km is, which of the following are true? Km is dependent on the enzyme concentration. No, this is not right. Km is independent of the enzyme concentration, right? Vm does not vary with enzyme concentration, wrong. Vm varies with enzyme concentration, yes. So B and D are the right options. Okay. I will solve this again for you guys to understand, because some guys might have missed the tutorial classes, like lecture classes. So I'll just solve how this Vm and Km has been derived. Okay, so we'll go into that. So we know that this is the equation K plus S giving rise to the intermediate, that is Ks. So for this forward reaction, K1 is the rate constant, whereas for Ks getting broken down to E plus S again, the rate constant is K2, and Ks being broken down into E plus P, that is the product, the rate constant is K3. Okay, so for rate of generation of ES, so ES, for ES being generated, what is the only forward reaction is only possible? E plus S giving ES is the only reaction. So from there, we are writing K1 into E plus S into the total volume V. Okay. And for the conception of Ks, there are two possible ways. Okay, Ks can be again broken down into Es, and Ks can be broken down into E plus P also. So what is the reactant here? Es is the reactant for both the cases. So how it will be? K2 into ESV plus K3 into ESV. So that is for conception of ES. So how to find out when your Rg minus Rc, that is nothing but your generation minus consumption is equal to accumulation, and here we say accumulation is equal to 0. Okay, as steady state conditions. Okay, so by taking off this as well as this, like multiplying minus inside both, so we are just getting minus K2 and minus K3 in the consumption what to say, in the consumption equation. We are just going to rearrange this equation. So how we are going to do? Step 1. So just keep the minus everything, like what to say? Yeah. So keep K1 on one side, make sure everything is positive. Bring the K2 as well as K3 on the other side. Okay. So the VV will get cancelled in the overall equation, right? V will be on both the sides. Okay. Whereas K2 plus K3 into Ks has happened. Okay. So now considering E is equal to, that means enzyme at that time is equal to total enzyme concentration minus the enzyme substrate complex. So either the total enzyme concentration you're giving at the start of the experiment. Okay, whether it can be present as evenly or else it can be present as Es. That's what this equation denotes. So what they are going to do, they are going to convert everything in terms of Et. Okay, so here by substituting this in the previous equation, we are getting Es is equal to K1 ETS divided by K1S plus K2 plus K3. So by again by rearranging, we will just come back to this equation. Es is equal to ETS divided by K2 plus K3 divided by K1 plus S. Okay, so this K2 plus K3 divided by K1, this is what was transformed into Km. Okay, so that's what transformed to Km. And rate of product formation, what we know, Rp is equal to K3 into Es. So this is what rate. So here we didn't write, here we just wrote rate of generation of Es, rate of consumption of Es, and another one is also there that corresponds to 3. Okay, product formation, for that what is the substrate? Es is the substrate. Rp is equal to K3 Es into V. Okay, so we know that what is Es, we have already found out it here. So we are just substituting over here. So K3 into ETS divided by V. So by substituting, by taking B to the other side, Rp divided by V becomes your V is equal to Vm, S divided by, so your what to say, your Vm is nothing but K3 into Et, and your Km denotes K2 plus K3 divided by Et. So if you go back to the previous equation, that's what I have written here as well. So if you derive this Michaelis-Menten equation, you will find out what is Km as well as what is Vm. So with which we can find out like which is right and which is wrong in the solutions that are being given here. You can go through the lecture for a detailed explanation of this. So question 4, match the following inhibition types in A according to the binding of inhibitor in B. Okay. Yeah. What are being given here in the option A? Uncompetitive inhibition, non-competitive inhibition, and competitive inhibition. Okay, so this is also a bit tricky until and unless we know the equations or we know completely the theory, we will not be able to figure out. Even if you know the theory, it's completely fine, but if you just see the equations directly, it will be very easy for you to understand what is a non-competitive inhibition means and what is a uncompetitive and what is competitive inhibition means. So on the B side, what they have given, inhibitor binds to the enzyme alone, inhibitor binds to ES complex alone, inhibitor binds to both enzyme and ES complex alone. So we have to just match what does each inhibition mean here. So what is uncompetitive inhibition? In uncompetitive inhibition, what happens is that we know this is the normal equation, right? Like the basic equation is E plus S giving rise to ES, and ES will be broken down into E into P. Your ES can be broken down again in the reverse direction to E into S as well. So there are two possibilities for ES to get broken. So in this uncompetitive inhibition, your inhibitor can only target the ES complex. Okay, it cannot it will when E and S binds, then only the binding site for the inhibitor like opens up. So it will go and inhibit just the enzyme substrate complex to further getting broken down into the product. So that only the uncompetitive inhibition can do. So for uncompetitive inhibition, what we can say, just a minute, let me take, yeah. So uncompetitive inhibition is nothing but inhibitor binds to ES complex alone. Okay. Non-competitive inhibition. In non-competitive inhibition, E plus S, so that is the main equation, E plus S giving rise to ES, that is getting broken down into E plus P. So this is the equation if any inhibitor is not being present in the the enzyme like what to say your reaction. Okay, in non-competitive inhibition, E plus I can give rise to EI, ES plus I can give rise to EI. Okay, so which means your inhibitor can bind to the enzyme like just sirf enzyme, like just enzyme is there, it will have the inhibitory property to even go and bind to the enzyme alone also, or else it can go and bind to the enzyme substrate complex also. Like in either way, the substrate, the binding sites of inhibitor and the substrate will be completely different. That's what I'm like trying to mean here. Okay, so the inhibitor will have a separate binding spot rather than what it's not going to compete with the substrate at all. Okay, so it can go and bind to the enzyme when it's just present as enzyme also. Even if it is going and binding with the enzyme substrate complex, the binding place for this inhibitor is going to be completely different. That's why it can bind even to the inhibitor, enzyme alone as well as enzyme substrate complex also. So for non-competitive inhibition, the right answer is inhibitor binds to both enzyme as well as enzyme substrate complex. So what is left out? Competitive inhibition where inhibitor binds to only enzyme only. So we'll check whether it's right or not. What is competitive inhibition? Where the main equation is being written and E plus I giving rise to EI. So which means it can just go and bind same as whatever it's going to whatever the substrate is competing for. Both substrate and inhibitor will have the same binding spot. So if the substrate has already bound to that, it cannot go and bind to that. Whereas it can just go and bind when it's just enzyme as such only. So the right answer is going to be for uncompetitive inhibition, it is Y. For non-competitive inhibition it is Z, and for competitive inhibition it is X. So the right answer is yes, A. Moving on to question 5, which of the following, among the following, which are involved in the estimation of cell concentration? Optical density, like hemocytometer, trypan blue, and blood gas analyzer. So we'll just see each and everything. So in case of optical density, we know, yeah, we can find the overall cell concentration if we use optical density as one of the parameters, right? Optical density is nothing but, for example, during the fermentation process, I will be collecting the what to say, your fermentation broth, varying from time to time. So at the 0th hour, there will be a certain concentration. How the procedure goes is that either you can just take, and then like from the fermentation broth, you can use the media as the blank also. So first you have to tell the optical density equipment. We call this as like any spectrophotometer to say what is 0. So we'll just give the broth alone, and sorry, the media alone, and set it to 0. And whatever the fermentation broth that we have collected at time like 15 minutes, 30 minutes, or like 1 hour, 2 hours, that we will be using it for calculating the absorbance. Okay, so absorbance corresponds to if the absorbance value is greater than 1, according to Beer-Lambert's law, we have to further dilute our samples, fermentation samples, and then we have to proceed. What is given here, it's 0.3, 0.7. So one thing is like when it comes to your optical density, it will not differentiate. It can just tell the total number of cells. It will not know, it cannot differentiate the live cells and the dead cells. That cannot be done. Whereas we can know what is the total cell concentration when it comes to optical density. Okay, so yes, it's going to estimate the cell concentration. And B is hemocytometer. We all know that hemocytometer is mainly used to like what to say, for cell counting only. So what usually for mammalian cells and all, what they usually do is that they'll be trying to give the media, like the cells at one corner, based on the number of cells that are present in each and every block. We'll just try to multiply it by 4, because all these are like equally split. It's just a guess that more or less those number of cells only will be present in 1 ml of cells. Okay, so with this we can differentiate, like it's just the cell counting, as I already told with respect to your optical density also. Whereas trypan blue, what happens in trypan blue is that this is mainly to differentiate your dead cells as well as your live cells. So wherever your like what to say, the complete blue spot has been taken up, those are like dead cells, whereas whatever the bright cells are there, those are like just the live cells. Yeah, trypan blue is also being used to differentiate your live cells and the, so to estimate the cell concentration only. Whereas blood gas analyzer is nowhere related to the cell concentration. It is just to analyze the gases that are present in the blood. Okay, so the right answers are 3 options. So sorry. So A, B, C, all 3 are right options. Okay. Moving on to question 6. Match the following microbial products in A to their appropriate choice in B. Spirulina. So as a spirulina, streptomycin, growth dependent products, and secondary metabolite, primary metabolite, biomass itself is a product. Okay, spirulina. So spirulina comes under biomass itself as a product here. Okay, because these are what to say, a nutrient that are being used for consumption also. So spirulina is like very nutritious, where the fermentation process has the only aim of producing high cell density. They have to produce spirulina at a very high concentration so that they can dry the cells or lyophilize the cells, and then they can further send it for the consumption. Okay, so when the there are many other examples like microalgae and many other products where the biomass itself is a product. In that case of in those modes of fermentation, the ultimate aim of the fermentation will be to produce very high cell concentration rather than focusing on the product, because here the biomass itself is a product, so our ultimate aim is to produce biomass itself as a product only. Okay, and option B streptomycin, and option C is like growth dependent products. So in case of your like growth profile, what will be there? Your lag phase, your log phase, your stationary phase, and your death phase. Okay, so during the lag phase, what happens? Your cells will get accustomed to whatever the nutrients in the media that are being given. It will just get accustomed to the environment, and the cell number will not get increased, but the cell size will start increasing. Whereas in log phase, what happens? The this is also called as the exponential phase. Okay, or the growth phase also. So your cells will grow exponentially, and whereas in your stationary phase, your mu will be equal to 0, because the cell death as well as your cell production will also be equal. So here just the cell concentration will be kept very equally. So why I started telling here is that, so option 3, if you see growth dependent products, so growth dependent products means that will come in the lag phase only, sorry, log phase only. Okay, so these are called primary metabolites. So when the cells are growing, for example, any say for example any mm, what are all the examples like here I can say is that growth dependent products are which are required for the cells to grow also. So there will not be anything that during this process, like it will not try to produce something that is not at all related for the cell growth at all. So during the exponential phase, whatever is being produced, the growth dependent products are called primary metabolites only. Okay, whereas the streptomycin, which is an antibiotic, that is called an secondary metabolite, because first the cells has to grow, right? Then only the cells will hear antibiotics. Say for example, your organism is being present in a nature's pot, okay, in the soil where many number of many other organisms will also be present. So the ultimate aim of organisms will be that first it has to grow. Okay, that will be the first ultimate aim. Then only it will think that all the other organisms are also competing for the like nutrients. So we have to produce something in such a way that the other organisms are dead, and only the nutrients are available for the organisms to further expand its growth. Okay, so in that case only your antibiotic comes into play. So here spirulina corresponds to Z, your streptomycin is an Z, X and Y. Yes. Moving on to question 7, define Ks in the monad model. Okay. Option A, Ks is the substrate concentration at which growth rate is half maximal. Ks is the substrate concentration at which growth rate is equal to 1. Ks is the substrate concentration at which growth rate doubles. Ks is the growth rate at which the substrate concentration does not influence growth. So this is also kind of very confusing, right? Like what we are going to do with this. So again, we will just write the equation. Mu is equal to mu max S divided by Ks plus S, right? So what they are saying, define Ks in the equation. So Ks is substrate concentration at which growth rate is half maximal. So everywhere they are saying, what if your Ks is the substrate concentration? That if your Ks is equal to S, what happens? So what happens? Mu is equal to mu max S divided by, when Ks is equal to S, 2S happens, S plus S, and SS gets cancelled. So mu is equal to mu max divided by 2, right? So where they are saying is half maximal, at which the growth rate is half maximal. So the right answer is this only. Okay, and there is a sorry, like 1 minute. Yes, I will just try to bring it here again so that you guys can see the graph. So what is happening here? So when the growth rate is, this is the when Ks is equal to S, what happens is that this corresponds to mu divided by mu max also. Like when the mu divided by mu max, that corresponds to Ks also. It's in the other way around. Ks is the substrate concentration at which growth rate is half maximal. Moving on to question 8. In the Monod model for growth kinetics with single limiting substrate S, the plot of substrate concentration versus growth rate S. So this is what we already saw, right? The same equation, the same graph only we saw here. But is it linear? No. And we don't know whether it's like, and it's not sigmoidal also. Sigmoidal will be how it will be, sine wave, right? It should be sine. Sigmoidal is something like this. Okay, sorry, that is sine wave, right? Sorry, sigmoidal is something that is different. So is it rectangular, hyperbolic, or else whether it's sigmoidal or it cannot be determined? We don't know any of these three answers. So what we can see is that we can just see the equations of rectangular, hyperbolic and others so that we can figure out. Okay. So first, what is mu is equal to mu max is divided by Ks plus S. For rectangular hyperbola, the equation is ax divided by b plus x. So here a corresponds to mu, x corresponds to s, ks corresponds to b, and then like again s corresponds to. So which means your monod growth kinetics, this graph like designates a rectangular hyperbola. Considering question 9, consider an enzyme substrate reaction following this Michaelis-Menten kinetics with the given data given below. Time has been given 5, 10, 25, 50 minutes, and what is the substrate concentration at the corresponding time has been given, and V has been calculated. Okay, so we have to find out what is Km and Vm. So we know that V is equal to V max S divided by Km plus S, right? So according to the Lineweaver plot, 1 by V is equal to Km divided by V max into 1 by S plus 1 by V max. So here this corresponds to your Y is equal to Mx plus C. Okay. So first we'll just plot the graph, and I have already done that for you guys. So we'll just see like how it works. So what we have to plot on the y-axis, we have to plot 1 by v, and then your x-axis 1 by s. So s and v has already been given in the equation, and what I have done, I have just taken the reciprocal of 1 like s, that is 1 by s, and 1 by v I have taken. So this is the x-axis and this is the y-axis, and then I have plotted the graph. And then when I saw the regression equation, like regression constant is completely fine, which is like 0.999, perfectly fine. Y is equal to, the equation has been given. Okay, again we'll go back to your. So this was the equation that was shown when we plotted 1 by v versus 1 by x. So 1 by s. So here what does that mean? Km by v max will be equal to 0.4577, whereas 1 by v max is equal to 1.8729, whereas like v max is equal to this one. So when we substitute v max in the other Km by v max, we will be able to find out the Km. Okay, so the right answer is Km and v max D. Moving on to question 10. Given the above data, what happens to the value of Vm if the enzyme concentration in the system doubles? Option A, value of Vm is quadrupled, value of Vm is doubled, value of Vm is unaffected, value of Vm equals to Vmax divided by 2. So we know that Vmax is equal to K3 plus K3 into ET. So this is what we solved in question 3, right? When we solved the overall Michaelis-Menten equation, we just understood Km is equal to K2 plus K1 divided by K3, and Vmax is equal to K3 into ET. So these are like almost, if you write it in such a way that Vmax is directly proportional to ET, right? right? So what they are asking, what happens to Bm if the enzyme concentration in the system doubles? So as it is like double, if this is going to get doubled, then what happens to this? This will also get doubled only, right? So the answer is double. These are like linear and it's very easy to understand also. So with this, the 10 questions of tutorial 2 has been solved, and if there is any doubt or something, you guys can always like get back to me. Okay. You guys can post your questions over there in the, what to say, uh, in my uh, email also. I can get back to you guys. Okay. Thank you so much. We'll see in tutorial 3.